All right, today we're going to be covering 3.1, what are congruent figures? So let's go ahead and jump right in. So first off, we have these two triangles here. We have triangle ABC, so we can see that right here, ABC, and we have triangle FED. Now, with this, we can see that some of these points map onto some of the other points, and we can see this through if I were to translate figure A downward, B downward, and C downward, they would all map onto points F, E, and D, respectively. So from here, we can see that point A would fall perfectly on point F. Because of that, we call those points corresponding angles, because these are angles of a triangle. So these are corresponding angles. Point B corresponds with point E, and point C with point D. So we have three angles that correspond to three other angles. Well, what that shows us is that these three angles will all be congruent to one another respectively. So A is congruent to F, B is congruent to E, and C is congruent to D. Now, this also works for side lengths. So corresponding side lengths should also be congruent typically if the triangles are congruent. So let's see that here. So every triangle has 6 parts. They have 3 angles, and they have 3 side lengths. Now, when we say two triangles are congruent to each other, so if I have triangle ABC and I say it's congruent to triangle FED, what I mean is that A is congruent to F, so those two angles are congruent, and it's because they're both written first. Angle B is congruent to angle E, because those are both written second, and angle C is congruent to angle D. So this is what we call a congruency statement, because I'm saying that one triangle is congruent to another. So this is our congruency statement. Triangle ABC is congruent to triangle FED. Now, with this, the order is extremely important because the order tells me which angles are corresponding to which angles, as well as which segments correspond to which segments. So if I look at my segments now, well, the first 2 pieces that are written in this is AB. So I can see A and B are the first 2 letters. Now in my other triangle, the first 2 letters are F and E. Well, that means that segment AB is congruent to segment FE. And we can see that right down here with the squiggly line here. So AB is congruent to FE. Now, that works for all segments that we can find in this triangle. So our next one, well, BC is written as our second and third letters. In our other triangle, ED is our second and third letters. Well, that means that BC is congruent to ED. Very similarly, and again, order matters for this. Lastly, we have the third and the first, and also the third and the first. And when I'm saying that, I'm talking about the letters. So I have CA is congruent to DF. So if these two triangles are congruent, then each of these pieces needs to be congruent, each of these corresponding parts. So all the angles, all the corresponding angles need to be congruent. All the corresponding segments also need to be congruent. Well, that leads us to a very specific term and a theorem that we'll use quite often in Unit 3. So that is congruent triangles imply that all pairs of corresponding parts are congruent in those triangles. Now with this double arrow, it also works the other way. If I see that all pairs of corresponding parts are congruent, so I see that angle A is congruent to angle D, C is congruent to F, B is congruent to E, and same with the side lengths, then I can say that those two triangles would be congruent. So it works both ways. Now, again with these two triangles, if our congruency statement is triangle ABC is congruent to triangle DEF, that means A is congruent to D, because again they're both written first, B is congruent to E, C is congruent to F. Now, also with the side lengths, those also will be congruent as long as they're corresponding pieces. So I can see I have small side A and small d are congruent. Small b and small e are congruent, and small c and small f are congruent. So that means that all corresponding parts are congruent, therefore the two triangles are congruent. Now, one of the most important things here is the order that you write these in. So again, A and D are both first because they are congruent to each other. B and E are both second because they are both congruent to each other. And C and F are both third because those are both congruent to each other. If I mess up my order, so I see that ABC is congruent to DEF, if I mess up my order and I switch the F and the D, all of a sudden these two triangles, this is an incorrect congruency statement. Because again, I need to have the corresponding pieces match up. A needs to be with D, not with F. So keep that in mind as you're working on these. We cannot have these little errors where these letters are not matching up with their corresponding parts. If you do, that would mess up your congruency statement and you would mess up the entire problem itself. So just pay attention to that as you're going through these. Make sure that your letters are all lined up, and the best way to do that is to check for angles. Because of course, if one angle is 42, well then the corresponding angle of the other congruent triangle would also be 42 degrees as well. So again, they should be the same measure, or you may even just notice, congruency marks. So if you guys see congruency marks, that'll be a big hint that, hey, those parts are congruent as well. Now, for right now, what we need is all 6 pieces in order to prove two triangles are congruent. So I need all 3 angles and all 3 segments to be congruent with all 3 angles and all 3 segments. If they're not, then I cannot show that those triangles are congruent. Now later on, I will show you guys a little shortcut that you can use, but for right now, this is stuck in stone. They all need to be congruent in order for us to say that those two triangles are congruent as well. All right, so this is also true for polygons. It doesn't only work just for triangles, it also works for polygons. So all pairs of corresponding parts are congruent means that all the polygons are congruent, and also if I have 2 congruent polygons, it means that all pairs of corresponding parts are congruent. So it works the same as triangles. Now, again, this is just corresponding parts, and I'm going to go ahead and write this out for triangles because this is something that we'll use very often. So corresponding parts of congruent triangles are congruent. Now, this is typically what we would use after we prove that 2 triangles are congruent, and I need to show that 2 other pieces are congruent. We would use corresponding parts of congruent triangles are congruent. Now, that's a mouthful. So we go ahead and we shorten it to CPCTC. Corresponding parts of congruent triangles are congruent. So this will be our shorthand whenever we prove 2 triangles are congruent, and then I need to prove that the angles, some other angles within those 2 triangles are congruent. That's when I would use CPCTC. So prove the 2 triangles are congruent, and then we can use this. And this will be used oftentimes in proofs. Almost every proof that we do in this unit will see some type of CPCTC as we learn more about it. So keep that in mind as well. This is something that you'll use very often. Almost every proof will have it, this chapter. All right, next up we have the reflexive property. Now we've covered this in the past briefly, but again, it's a very useful property for us. And in this chapter, it's going to be used constantly. It's often used as seen in this picture down below here, where it's shared by 2 triangles. So if I have a segment or an angle that's shared by 2 triangles, we can say that that segment or angle is congruent to itself. So I see that segment AC is in both triangles. It's in triangle ABC and triangle ADC. So it's in both triangles here. Now, since AC is splitting the 2 triangles apart and it's shared by both, I can say that AC is congruent to AC. That is the reflexive property. Now, if there was some space between these 2 triangles, so if I saw something like this, then of course this wouldn't be AC and this wouldn't be AC because they're 2 different segments. But if they share the same segment, I can say that that segment is congruent to itself, and it will be used a lot. So just keep that in mind. So right here, we see triangle KET is a reflection of triangle KIT. So here's KIT, and then here's KET. So I did a reflection of triangle KIT, did a reflection of KIT over segment KT, and that gave me triangle KET. Now, I want to map all my pieces together. So first off, if I reflect over segment KT, angle I maps onto angle E. Angle 1 maps onto angle 2. Angle 3 maps onto angle 4. And then segment KI will map onto segment KE. Lastly, IT will map onto segment ET. Now, do I have all 6 pieces to show that these two triangles are congruent? Well, no. I have 1, 2, 3, 4, 5. What am I missing? We're missing that KT is congruent to itself. So we can therefore say KT is the 6th part because KT is congruent to KT by the reflexive property. Again, it's shared by both triangles, right? It's a side length on both triangles. It's a segment on both triangles. So I can say that it's congruent to itself. All right. Now, this is the reflexive property with angles. So I see that I have triangle PQR, so this triangle right here. And then we have triangle SQT, this triangle right here. Now, we see that they both share this angle up top. So I can say angle SQT is congruent to angle PQR by the reflexive property. Now, could I also say that angle Q is congruent to angle Q? Well, yes, because there's no other angles attached to angle Q, so that works perfectly fine. But I would suggest trying to be very specific with these unless there's nothing else surrounding it, in which case you can just simplify it. But using all 3 letters will ensure that you're getting a very precise answer and making sure you know exactly what angle you're talking about as well. Especially if there's multiple angles, so say that this continued on, then there's 2 angle Qs, right? So we want to make sure that we're very specific if needed. But for this one, you can use either answer depending on what they're throwing at you. All right. Now, just a quick reminder, because this is a good way for you to be able to show that 2 figures are congruent at any time. If you have a rigid motion, meaning a translation, reflection, or rotation, that will map one figure onto the other, we automatically know that those 2 figures are congruent. Again, dilations do not work because dilations change sizes, and congruent means that they have the same measurement. So if I need to change the size of the shape, it's not going to be congruent. So just keep that in mind. Dilations do not work. Only reflections, rotations, and translations will be the rigid motions that we can use. Now, we see a rotation of 180 degrees. So what I would like you guys to do is write the conditional statement, so finish up this conditional statement, and tell me which triangle it is congruent to. Be careful of your order when you're writing this out. And my big hint is pay attention to the angles. Now, if I'm looking at this, I see that angle H and angle H are shared by both, right? They're vertical angles. I know that they're going to be congruent. If I swing this around, H will just stay in its place. So my first letter will be H. I notice that point G is a right angle, so I go to my other right angle, and that's K. So G goes with K, which means that F must go with L, because that's all that's left. So therefore, triangle HGF is congruent to triangle HKL. And that's our answer. All right, let's go ahead and move on. Here is our final question for the day. Justify each conclusion with a property. So we're given that points M and N are midpoints. We're given that DC is congruent to AB, and that AB is congruent to DB. We also know angle 1 is congruent to angle 4, and angle 2 is congruent to angle 3. Now, what we're going to be doing is we're going to use this given information to write out reasons for these steps. So why can I use these steps? My first one, ADC is congruent to ABC. So ADC is this angle right up top here. ABC is this angle right down below. Now, why could I say that these 2 angles are congruent? Well, angle 1 and angle 4 are congruent. Angle 2 and angle 3 are congruent. What am I doing to get the full angle? Well, I'm doing the angle addition property. So that is the first property. If I see that we have these angles that are congruent, and I need to show that these 2 angles are congruent, the sums of those, that's just by the addition property. Next, we have CM, this segment here, is congruent to AN, this segment here. Well, I know that DC is congruent to AB. So that's the long segments. And I'm trying to find the short segments. So MC and AN. I also know that points M and N are midpoints. Now, if you see midpoint written twice, which we do, 2 points are midpoints, and that's it being written twice, then I know that that opens up the division and multiplication properties. So, am I going from a large segment to a small segment, or a small segment to a large segment? Well, they give me the large segments. I'm going to the small segment. So this would be division. If I'm going from big to small, it's going to be the division property. Next, we have segment BD is congruent to segment DB. Well, DB is here and BD is here. That's the same line. Oh, those segments are congruent by which property? Reflexive. The reflexive property says that any segment or angle is congruent to itself. And then lastly, we have DC is congruent to DB. Now, if I look at these segments that they gave me, they said DC is congruent to AB and AB is congruent to DB. Is there a way that I can just skip through AB and go straight to DB? Absolutely. What is that property called? Well, that is the transitive property. I'm skipping that step right in the middle, and I'm going straight from my initial segment to my end segment. So I'm skipping through AB, which means that this is a transitive property. All right, with that being said, we are now finished with today's notes. If you guys have any questions, please let me know. Thank you guys so much for watching. I'll talk